Hello, good afternoon. Welcome to the stream. It's another Sunday. We are going to be doing register allocation today. I'm very excited. We got to start on it last time. We did, determining the live variables in each procedure. One procedure at a time. And today we're going to figure out how we can take that information, determine what registers are available, and what variables interfere with one another, and then we will do some register Sudoku. And I've been alluding to this since last time. I think it's a pretty fun concept. It's really for the longest time, this idea of register allocation has been kind of mysterious to me. And I think what's really great about the book that we're working on, I'm going to show it again for the nth time, Essentials of a Compilation and Incremental Approach in Racket, except we're doing it in Gleam because I love Gleam. And I'll be using the PDF book on the stream so you all can see that when you're here. Anyway, what I've been alluding to is that when you go to assign variables to registers or locations on the stack, in this case we're compiling to x86, so that's the sort of mental model we need to have. So when we're assigning them to variables to registers or to places on the stack, you do this kind of approach of figuring out what things are live at the same time, which we already figured out what variables are live last time. And you declare those things to be in conflict with one another. So in other words, if variable A and variable B are alive at the same time, they can't live in the same location. So whether that be memory or register, right? And that just kind of makes intuitive sense. Because you might use one and then use the other, and you can't have them living in the same place if they have different values. So the next step is when you have that set of conflicts, like these things have to exist at the same time, and so they can't be put in the same location. Then you go through and you figure out, well, what locations could they be put in, or could they not be put in? And this brings the calling conventions back in, the x86 calling conventions, as well as like the registers that we know should be available for use within a single function. So, and then you walk through the graph and you pick places to put things, and it's a really interesting discussion in the book. I've read it about 3 times now. I think it's starting to sink in finally. But we're going to get started on it today. So first, let's switch over to the coding, and I'll show you what we were doing last time, just to review. So we were doing this pass called Uncover Live, which just takes a x86 program and returns another x86 program just by adding an annotation, right? And that annotation is for every block in this program, we have the set of, or the list of variables that are live after each statement. This also includes the before for the first statement. So the way that this is working is that we start by iterating over the list of instructions from back to front. We know that at the end that REX and RSP are live because these are registers. So we're talking about locations, not just variables, right? These are registers that are used in the calling convention, right? You have at the beginning you have moved RSP, so it's live. Because you needed to allocate things on the stack, or you needed to push the previous base pointer, etc. Hi, Chris. Welcome to the stream. Thanks for joining. And of course, RAX is your return value for your function. So like that has to be live at the end. So that's where we start. This is the live after for the basically the return. And then we iterate over it backwards. So we're doing fold right, and we are going to add new live sets on the front. So when you have the live after, and you take into account the instruction for that live after set, you can compute what's live before. Okay, so that's how the algorithm works. So here we're doing the before set is, so if we have like this is a set of locations. We subtract the right locations that are involved in this instruction, and then we union the result with the read locations that are in this instruction. This gives us the next set. And inductively, the before set of a single instruction is the after set for the instruction before it. So in this way, we construct the entire list of live after sets. And this, then we have some helper functions there. What are the locations that are in this argument? Obviously, an immediate has nothing. A register has just that register, and a variable just has just that variable. And then you can look at the individual instructions that we have that we support in this subset of x86 assembly, and you can kind of see how this builds up from the locations that are in each argument and so forth. And we know, for instance, that popq includes RSP, and then pushq includes both the thing in A, so you're reading from that, and then you are also including RSP because it's changing. So remember, you can think of pushq as move its argument into the position pointed at by RSP, and then subtract from RSP. So that's why these are read locations. And then call Q, we include all of the saved registers for a call. Those are considered read from. These are I'm sorry, these are not the save registers, I believe. These are the argument registers. Yeah. And right, these are the argument registers, and then you take whatever the arity is. So if it's arity 0, obviously you have none of these registers read from. But if you have arity 1, arity 2, and so forth for a function, then you're going to be reading your arguments from these registers. And they're only supporting up to 6. Everything else is passed on the stack. So we don't account for any functions that are over arity 6. And then return, we're going to read from RAX. I have these question marks. Is this correct? And jump, there's nothing read, nothing written to in this instruction, so we just jump. There's some questions here we may come back to. And then lastly, what things are written to in each instruction. Remember, x86, the target or like the output of an instruction is always the rightmost argument. So for add q, it's B, sub q, it's B, and so forth. Call q, obviously, what happens after call q? You get a return, and so whatever the happens inside that function you call is going to write into RAX. So this is a right location for that. Move q, neg q, pop q. Remember, pop q and push q both involve moving RSP, changing the value in RSP. So that is a right location. And then for push, I'm not sure why that has a... Okay. Anyway, I don't remember why push Q has this as a right location, because you're not writing to A. You're taking from A and pushing it. Whatever. I don't think that this is strictly incorrect, but we might discover some problem with that later. Okay, so this is what we did last time. So today we're going to look at creating the interference graph. So, whoops, here, have the book up. So we know where each location is live. We need to answer this question: are locations U and V live at the same time? So, are these two variables, are their lifetimes overlapping, basically? And they say, to make this question more efficient to answer, we create an explicit data structure called an interference graph. An interference graph is undirected, and it has a node for every variable and register that has an edge between two nodes if they are live at the same time. That is, if they interfere with each other. Okay, so they're saying use the Racket Graph package. We have a package in Gleam called Graph. It's not part of the standard library. It's very simple. It's just adjacency lists. However, the adjacency lists are stored on the node in the graph, and underneath it, it's just a dictionary. So let me turn the fan on. It's a little warm in here. Okay. So we're going to use this. I'm going to add it to our project. Gleam add graph. Okay, so we added the graph library to our project. And I think so one of the challenges with this is that we have to figure out what this should be. So we might need to create a structure that wraps this graph data structure, and we will assign integer IDs for things, so that it'll be a little bit easier. Like, this is it very much expects you to keep track of what the IDs of each node are, which kind of bugs me. If I were using the Erlang digraph module, which is based on ETS tables, we could also bind to that if we want. So there's digraph. You can add a vertex, and the vertex is just a term. So I think. Right, so the created vertex is represented by the term $v atom n, where n is an integer greater than 0. So, and this is an improper list. Fun stuff. I think they were doing that because, like, this was cheap. In an older version of Erlang, this was cheaper than a tuple. I don't recall why. Okay, so that's an unlabeled vertex. This is where you have a label on it. So v, right. So here's the final thing. So creates or modifies vertex v of digraph g. So v is I guess whatever you want on it. Regardless, it picks what that vertex is, potentially. And then you can add and delete edges, and it looks like kind of an imperative API, but it's it's ETS tables underneath. So I think I still want to go with this. It's a very clean implementation. There's not much to it. Yeah, so let's go with that. Yeah, so we're gonna make a pass, and what is it called in here? So what we're going to do is a pass called build interference. So that's what we're gonna call build interference. Okay, and then we're gonna import graph. The other thing I mentioned we might want to do is create we're going to go ahead and make this. So this is going to import EOC langs x86 var as x86. Okay, so we're going to take a program. Again, this is going to be very similar to our others. Program. There we go. I don't know why I can't type that. And it's going to return a program. And we'll put a to in there for now. So we will work our way through this. Okay, so this assumes that we have we've done the liveness analysis from that uncover live phase. Okay, so we're going to do this graph thing for every block. So this is going to be very similar to what we did before. Actually, we'll do program .body. And this is going to be, this is a dictionary, so we need to import that. Map, we're going to map values. Right, so that takes a function, and we're going to ignore the key, and we're going to take the block. And then we're going to put that back into a program. Okay, that's pretty typical what we've been doing lately. Okay, so this needs to return a block. And what we need to do on this block so what is the contents of this block? Yeah, block. We're going to destructure it. So it has body and live after. Obviously, we could do that with dot accessors. So then we're going to, we need to add something to block, right? Which is the interference graph. So let's go and add that. Okay, so we're going to add this. This is the, what are they calling it in here? Conflicts is what we want to call it. Right, so it puts it under the key conflicts. Now we've been kind of treating this as, you know, an open book and just adding things to it. What we might want to do is create like a block info type and just add fields to that rather than this. Excuse me. But for now, if this doesn't get too long, we will, yeah, we're going to import graph. We'll just keep adding it to here. So this is going to be a graph, and this is going to be undirected. So let's look at that type there. So it has direction. This is going to be undirected. The value, we're not sure yet. So what's the where does the label come in? Each node holds a value and each edge has a label. So I think we're going to go with nil for the label. And the value will depend on what we want to do with in this interference. So maybe what we do is let's define this in build interference. So we're going to say pub type interference graph, or we'll just call it conflicts. And I wonder if we can make it be type alias. Yeah, seems to like that. Okay. So we want this to be undirected, and we want let's just make an empty type node here, and we'll just say node is the value. Well, maybe we'll turn this into a struct or something later, and then nil is going to be the label type. Okay, so over here we can just say build let's see. Yeah, we don't need this anymore. So we'll do import EOC passes build interference. And we'll say conflicts. We're going to import just that type. So this is conflicts. Okay, so now that I've added this, it's going to break a ton of things because we have to populate that in all the places that we're adding it, which is sort of like maybe we should have made this info as a struct of its own. But let's see. Oh, it forms a cycle, so we can't actually do that. Let's make a second module, or rather a third module, and let's extract that. So interference graph, and we'll just put it in here. So we'll say that might actually work out better anyway, because we have the possibility of let's call it graph. We have the possibility of putting utility functions in here that'll be useful for us. So this is going to excuse me. Okay, so then over here, what we'll do is we'll say interference graph.graph, and we'll change this to EOC interference graph. I have the feeling we're going to get more of these utility. Yeah. Okay, so now what do we got? Expected 3 arguments. This right. So here we are. Let's restructure this such that it assumes that that thing is there to begin with, and then we was this select tail? Oh, this takes a C bar. Okay, so here we're gonna do. Let's okay, so then we can just do where did it go? Yeah. Okay, so then we've imported it there. And then the other places where it occurs, yeah, so we have a bunch of literals in our test. The other thing we could do here is make a function that's new block and just returns an empty one, and then we can do splat updates on it. That might be kind of nice. Oh, well, yeah, let's just remove that like so. Okay, so let's do a new block. And this is going to return a block. And it's empty list, and interference graph new. Okay, so then in the other places where we have issues, we can go, it's like here we can do and remember, we're going to redo assign home, so this is kind of not all that important. But we could do var.block and say body is this var.newBlock. I think that's how the syntax works. Let's just say base block var.newBlock. Yeah. How do we do that? Wait, why did it not update? We changed this. What's wrong? I was not expecting one of dash. Oh, Here, let's do that and then go. I saw this earlier, I promise. Okay, Gleam, splat. Let's see. Let's just go to the docs, the language tour. Because there was a kind of splat update for structs. Data types, records, record updates. Okay, so you have to put it first. So let's do base block, and it's ... and then we give it that. Okay, so it has to come first. All right, let's see what else is broken real quick. Okay, so in the other test, so we'll do let base block is var.newBlock, and then we'll do base block, comma, and this needs a keyword body. Okay. And that means we can remove this extra down here. Okay, what else is broken? Okay, expected 3 arguments got 2. Right, so we're gonna say this is conflicts. Now we could instead just do that and ignore the conflicts for now, because we only care about these when we're going to compute. And then we can say let conflicts is you know, what do we call this? We're calling this build interference. I don't know. I'm going to make a function in here called determine conflicts, and that's going to take the body and the live after, and then we'll do x86.block block, and then conflicts is in there. So this function determine conflicts it's going to take the body, which is a list of x86 dot instructions, right? And the live after let's close some of these things. Right, instruction, and it's going to be a set of locations. A list, a set, list of set locations. Okay, and this needs to be x86.location. We need to import Gleam set. Nope. What was that? Yeah, it's just Gleam set. I don't know why the language server is being funky. Okay, and this needs to return an interference graph. And we will import that. And honestly, I think, you know, at some point we're going to have to import everything. Yeah. Okay, so that has a to-do. All right, let's look at the algorithm. Now that we have the basis here, I'm assuming we're going to do something like loop over the body or loop over the live after, probably in concert with one another. And I think that this may be a case where our last pass produced too much and we need to like take the tail of this. So like remove the first one, which is the before set of the first instruction. But we'll find out. So the other thing we could do potentially is zip them together and loop over the right of them, like fold right. Okay, so we're gonna say we're just gonna make a new graph. Honestly, this is, you know, what we'll return to begin with. But this might be the accumulator in our fold. However, I get the sense we might need some other things to give us what am I trying to say? To give us the like accounting that we need to keep track of things in here. So okay, let's read a little bit from the book and then we'll get into this. Okay, remember, an inference graph is an undirected graph that has a node for every variable and register and has an edge between two nodes if they are live at the same time. So interestingly, what we should do before we start is probably add all the registers, right? And maybe that's what this new should do. Okay. So I think that the contents of this node, it's at least going to have a location, which is an x86 var location. Now, the problem with that is we get this circular, node. We get a circular import. The other we could move this to a different module. And I've been thinking about for a while that things like register between the different variants of these languages, register doesn't change. It's always the same. Maybe it should be in its own language that's imported into here. I don't know if I'm ready to do this refactor, but that could be useful. And that, with the circular imports, the problem is you just basically need to make a new module. So let's see if nope. Okay. So let's make a new, and we're just going to call it x86. I know that's, let's say x86 base. And then I'm going to put location in there. Okay. And I'm also going to put register in there. Oops. And now these are independent. But what I need to do is we need to import that, and we're going to import register and location. Okay. And now there's an issue here where we have it defined here as well. So I think we don't need location in this file, but we do need register. So I think I'm going to move that, and then we'll fix the compiler errors. Okay, so now there's going to be issues where, yeah, there's still an import cycle, so we'll do base here, and this is as x86. This is just x86 location. All right. Okay, so we'll say type. And let's see, location. Right, location is only type. Okay. And here, the interesting thing is these are now the same. So where are we using this? Find all references is not working. So this is a private function. So where's the translate register? Translate reg. Okay, so it's here. Now that these are the same type, we can just remove that call. Of course, we weren't doing it there, but we can completely delete this function because they're the same type. All right. Module x86 does not have an RVP value. Yeah, so up here we need to do RVP. I'm trying to remember if there's anything else in here. We'll just import it directly. Don't care. Okay, so here this needs to be x86 base register, and we will import that. and let's just fix this with some control, yeah, Command Alt base. Okay. Let's open up the floodgates of all the errors. Okay, so yeah, so we need RBP and RSP here, and we'll just unqualify those. I told you, like, I really didn't want to do this refactor, but I think it's necessary. Right, so this, let's go to that file. Yeah, and RSP, REP, RSP. Okay, so there we go. All right, and then that's RSP, REP. Okay. Anything else? Ah, we've got more. Okay, so patch instructions. And we need RAX. That's the only one directly referenced. Okay. Kind of like this anyway. Not gonna lie. Okay, that aside from just removing that potential circular dependency, this is also good because now there's no translation between types which essentially have the same values. So, okay, so here, oh gosh, we've got to do it everywhere. Let's see, Lang's x86 base. And then let's see, we just need RAX. Okay, RAX. And then we'll go and we'll find all these and replace them. The squiggles will be our guide. Okay. You know, it's funny, I used to be, if you're, you know, new to my stream, you might not remember, I used to be really heavy Emacs user. And I tried out Zed early on my stream on a whim, partly because my, oh, in here, we need to fix it in here. My internet pal, Quinn Wilton, suggested it, and this is like 2 years ago now, nearly. So that we could, you know, work on the same buffers at the same time, because it had that collaboration feature. We need RBP as well. Okay. And then it's like, oh, this is fast. This is really well integrated with language servers, not kind of like works half the time, crashes the other half. So it was really a breath of fresh air, and I was sort of annoyed. I didn't want to go to this, like, I was so into, you know, key chords and everything. I was really good at them at that point, and I still have that muscle memory, and it like trips me up from time to time. But I have no regrets. Like, even though, okay, so now we've got x86 base location. We just need to okay. Oh my goodness, I thought I just fixed everything. Okay, so can I make this go faster? We need RBP and RAX. Yeah, Zeb was fine as an editor, and that single page rip grep edit is really nice. Yeah, and I actually need to just take advantage of that. It's pretty dope. Like this view. It's not for everybody. I know like some people have a really heavily customized VS Code flow or NeoVim or whatever. The lack of custom theming and zooming font size was what kept me away. Well, like this, or picking a theme. Is that what you mean, Chris? Yeah, it's not as like VS Code has a way bigger community for sure. Okay, so I'm gonna say, oops, not all files, just this file. We're going to replace x86.rbp with rbp. Let's replace all. And then we're going to assume with rex. That's a bit faster. And we have RSP as well. And then we just need to import RSP. Okay, that was quite a bit faster. I need to do that from now on. All right, it's all these freaking tests. Notice sidebar not zooming. Oh, yeah, the UI zoom is problematic. I don't know a solution to that. Okay, x86 RBP. We're going to replace with RBP. And REX with REX. I need to be importing this. REX, RBP, probably need RSP. No, it's not in this file. Okay, so we don't need RSP. All right, what else is broken? Oh, okay, so I'm surprised we didn't see that before. This block thing. Okay, so let's do let base block is that is the x86 language. Okay. New block. And then we'll do base block body, and then we'll delete this other bits. Okay. And here's an REX. Okay, so we need to get that in here. And we'll just do it. Okay, and we need to do the same bit down here. And we'll delete that. I think this is better anyway because, like, even with having to like put this in all of our tests, every place we do that, like if we add other things to this block structure, like more fields, we won't have to change our tests as often because they'll just be like, well, if I don't care about those things, then I'm not going to set them, and that's probably better for us longer term. Okay, so right, so this is just an import problem. This is just moving the types to look and loc reg and loc var. Okay, and then this we only imported block. Okay, and here let's do RAX and RSP and just unqualify those. And here's RSP again. Okay, so the other thing we could just fine. Let's just get all those. The other option here is because we didn't, oops, we just moved them to the other module. We can do that. That'll save me some time. It's not consistent, but it'll save me time. Okay, and there's another REX. We are slowly breaking them down. Okay, so here we need to do, what we're going to do is ... block, and then we're going to do live after and just overwrite that. So that's nicer in this place too, if I can type it, because then we don't have to care about the contents of that graph, which is empty at this point. 77? Are you kidding me? Oh my goodness. Okay. It never ends. Like, this is one thing I appreciate about Rust. Like, it'll show you immediately where everything is for the most part. And the language server is way more sophisticated. Okay, down to 4. Right, so here we need to do let base block var dot new block, and then we'll do body is instructions. We don't care about the rest, and this is base block. Body is instructions and live after, live after. Note this syntax. It's kind of like, yeah, 90 327. I know that feeling, Chris. Okay, so this syntax is sort of like JavaScript TypeScript struct update. Where it's just like, if the variable is the same name as the field, then it just gets in there, except that in Gleam you have to put it in a colon after, and then if you're not putting a value after that colon, then it just takes the local variable of the same name. So okay, another one in here. So oops, let base block x86. Okay, and then we'll do base block body, and because Gleam, like Elixir and like Erlang, is basically immutable, your updates are always creating a new value, so you don't have to worry about, oh, well, I'm using this base block twice and then I'm mutating it, and, you know, am I updating the thing? No, there's no mutability there. What are the 2 warnings? Okay, so that's fine. That's where we are. All right, just for sanity check, let's run tests and make sure I didn't break anything. Okay, so just the warnings. That's fine. Whew, what a refactor. But we'll be better off. So I think I'm going to get rid of this pattern match, and we're just going to do block.body and block.liveafter, and we can get rid of that. The other thing we could do is collapse this into here. I think this is fine for now. Okay. Now to the problem at hand. So Okay, so let's read here. Interference graph is an undirected graph that has a node for every variable and register and has an edge between two nodes if they are live at the same time. That is, if they interfere with each other. We recommend using the Racket graph package to represent interference graph. Well, we're using the Gleam graph package. Okay, so a straightforward way to compute the interference graph is to look at the set of live locations between each instruction and add an edge to the graph for every pair of variables in the same set. Okay, so this is less than ideal for two reasons. First, it can be expensive because it takes O(n) squared time to consider every pair in a set of n live locations. Second, in the special case in which two locations hold the same value, because one was assigned another. So like, think of like move from a variable into a register or move from one variable into another variable, then they have the same value. They're not in conflict, right? Okay, they can be live at the same time without interfering. So they say a better way to compute the interference graph is focus on writes. And this comes from a paper from Appel, no surprise, big name in compilers, from 2003. The writes performed by an instruction must not overwrite something in a live location. So for each instruction, we create an edge between the locations being written to and the live locations. So we may need to use the function that we did here in uncover live, which is write locations in instructions. To get that. So maybe we'll go ahead and make that public. Okay, so create an edge between the locations being written to and the live locations. However, location never interferes with itself, of course. For the call queue instruction, we consider all the caller saved registers to have been written to. Caller saved. So an edge is added between every live variable and every caller saved register. Okay. So there's some initial setup here. So also for move queue, there's a special case of two variables holding the same value. Right. Okay, so if a live variable is the same as the source of the move, then there is no need to add an edge between variable v and the destination because they both hold the same value. Okay, so let's first make this public, and then we can use this in the other one. And this may actually be a place where we need to look at push queue. But I think that we're not generating any pushes yet, except for in the prelude and conclusion. So we may need to revisit that again, like I said. Why do we care about push queue? Why is that location for push? You're reading from it. You're not writing to it. I am convinced that this should just be this. We probably don't have a test covering that. No, we don't. Okay, so I'm going to go with my gut feeling on this. You're pushing a value from this location. You're not writing to it. Okay. Here. We have a lot of stuff open that we didn't intend to. Okay, we're going to close. Okay, we can leave that open because we're probably going to use it. Select instructions, assign homes, we don't care. Okay. We will want to probably modify this. And what we need to do is populate it with all of the registers. we'll probably want to make a like something that keeps track of the integer IDs of the nodes. Okay, let's look at these rules. So if an instruction is a move instruction of the form move q from S to D, then for every variable in the after set, live after set for this instruction, if V is not D and V is not S, then you need an add an edge between D, so the destination of this move, and V. Okay. For any other instruction, for every destination in the right set and every variable in the after set, if V is not D, then add the edge. Okay. So this is the essence of our algorithm. So they are working from top to bottom. I think that they're not working back to front. And that's fine. I think that probably we need to fix this such that it doesn't produce the extra it doesn't produce the extra one. Which to me says that we could just do list.tail. Or is tail TL? Is that a built-in? Yeah, that's no. Yeah, it's not. There's no head or tail. What even is this language? All right, let's look at lists. I mean, we can do let do it like that. We probably need a let assert there and do tail. Like then we're going to get, we only compute, because inductively the before set is the after set of the previous instruction. We don't need to generate this. Now this is going to break our tests because we had, yeah, like we're producing an extra one in the test. So what we need to do is just remove the extra one from here, from all of our tests. And then we should get, yeah, it passes. Okay, so I'm okay with this. It's not the best, but I think that if we have the same number, so if we're looking at here, if we have the same number of live after sets as we do instructions, then it's going to be way easier to do this thing. So so let's start by zipping those instructions with the sets. So I'm just going to call it pairs because I don't have a zip. And we're going to zip body with live after. Okay. And now we can I think what we should do is assume that the interference graph has all the registers in it, and we'll put that in interference graph new. So we can just turn this into a pipeline. Zip them together. Come on, Sean. Okay, and then we'll fold, and the new interference graph will be our accumulator. And then our function, which takes the graph, and it's going to take a pair of instruction and I don't like shadowing that, but we're going to shadow it. It doesn't like that destructuring in the function head, so we'll say pair. And then we'll do to do there. Okay. Where's this? Let's go away for now. Okay. So maybe I'll make some functions that are like rule 1, rule 2. And they take, yeah. So let's do case instruction. And does it not know what that is? How does it not know that that's... So if it's a move, and we'll use their variables here, we're just going to say rule 1, and that's going to take, it's going to take S and D and live and G. Or maybe we put G first, because... And then for every other instruction, okay, so this is where we use the write set. For anything else, we do uncover live dot write location in instruction. We need that. So rule 2, and we'll pass the graph, and we need the live set. Okay. Okay, so let's make these functions, and then now if this not to do, it probably knows what this is. No, it doesn't. Okay. So rule 1 is going to take interference graph, So this is going to be G. It's going to be interference graph.graph. And it's going to take S is a location. D is a location. And live is this. And it might be worth making a type alias for that. So it's got to be x86 base location. And this is going to return the graph. What a type signature. Okay. Okay, and then let's spec out rule 2 as well. Yep. Okay. It's inferring things correctly. I just wanted to make sure. So this is going to be, oops. All right, so this is not a list. This is just a set in this case, right? Okay, so this is going to have the same. And this is going to be the right locations is going to be a set, a location set. And the live is going to be a location set as well. And this is going to return a graph. Oh, no, to do, please. Okay. Okay, so now, not lists, list. Little typo there. Okay, so that's the overall pattern that we're going to do here. Is this x86 var? Okay, so did we have something that we converted things into locations in Uncover Live? Have a little helper function? Or did we just... yeah, we just manually did it. Wait, hold on. I see we did it like this. Okay, well, let's do something similar to this over here. And we'll just go, we'll call arg to location. And maybe that means we just treat all of these as sets of locations that potentially have one. I think that's probably the wise thing to do. That does make it a little bit trickier. The thing is, though, for moves, yeah, let's do location in arg, and then why don't we, or locations in arg, why don't we just export that from Uncover Live? Okay, these phases are kind of closely related, obviously. Yeah. And let's do uncover live dot locations and args for D. The problem here I'm seeing is if like you can't have an immediate value here, but you could here in the source. So this needs to have the possibility of being an empty set. In which case it doesn't conflict with anything, obviously, but you need, like, we can't. The other option here is that we could just pattern match everything. And only consider, like, we could create special versions of rule 1. Like, if this is a variable or a register, then call let me think about that. Yeah, let's do that. I this feels like a problem. Okay, so let's pattern match on this. So destination always has to be a variable or a register. Let's pattern match on immediate and just say, like, we'll have rule 1b that only considers the destination. Can we do that? Okay, so if the variable is not the destination of the source, add the edge between. Well, let's just make a rule 1b and we'll call it. That's destination, and we need to pass live. And can you add missing patterns? Okay, I want to get all of the move cues up here. And then the rest of these we can just dump them because they go to rule 2. Okay, so we need this, but a register, location register, and here this can never happen. We generate that, we need to panic. I don't like putting that in there, but it's worth. Okay, so then I'm going to rename this to D in both of these cases for consistency. And this is S and D and S and D. Okay, so here we'll do rule 1, and these I'm going to change back to just locations. Okay, so this would be calling rule 1 with G, and this is a register. Location register. One thing I'm expecting us to run into with this graph package is that you have to know what the index, like what the integer index or key is in the graph. And I'm like, can I use any other value for the key? Like, is there any reason why this can't be a key? I don't see why. Okay, so now we've actually turned it into the right thing. Having sets was just going to make it a pain in the butt. And let's stub out this function. So this takes basically the same arguments except no s, right? And that's going to return a graph. Here, let's just fill that in. Okay. So right, so this means that D can only be in conflict with the things in the live set, whereas because you're moving from an immediate. Whereas in these other cases, you're moving from something that's not an immediate value into that destination. So, and here, obviously, if you're doing this, that should not happen. Okay. I feel like we keep getting distracted dealing with issues of the design, but like this is what this is about, right? And I really do want to get to graph coloring, but we might just get done with the interference graph today, which would be okay. Okay, so we're going to need some ways to, first of all, we need to populate the graph. And I'm going to say add registers. And we'll make that a private function. That's going to take graph and return a graph, right? So we will do I think we need to change this up as much as I didn't want to, because we need to be able to look up nodes in the graph by their location. So, but the interface to that, excuse me, the interface is that nodes have an integer ID. And when you insert a node, you have to provide that ID. So we have to do some extra bookkeeping ourselves. Let's do this. Graph is going to have, let's make a lookup table. and this is going to be from x86 location to int. We're going to have the graph inside, which is this. And then we're going to keep track of max ID, which is an int. Okay. So we're going to have to make a function which is insert location. And this is going to take location is going to be x86 location, and it's going to return the graph. And this will take care of our lookup table. So we're going to say next ID is graph.maxID plus 1. And then we will say this is going to be dict here. Location, next ID. And then we will make the node graph.node, and this is going to have, so we're using our own node. But the ID is going to be next ID here, and what is it, value? Yep, value is going to be our node with location in it. Oh, here's the problem we're calling this. Let me call this G. Just so we don't confuse it with the module. That's probably what's happening. So using their insert, let's just go to the actual docs for this thing. Xdocs. Okay. So type node, type graph. So we need to insert node. And that's going to be g.graph, because this is ours. And then we'll insert that node. And then we return our own graph. Okay, so I don't know what's going on here where it's like, I don't know how to tell you what the errors are because there's clearly errors in here. Oh, it's this. Syntax. Okay. Okay, so now let's do graph.new dict.new 0, add registers. Okay, so then we can go list.fold, and then let's list all registers, and we'll pass G in, and what we're going to do is use insert location. So these need to be locations. So let's pull this out. And I'm just going to list all the registers. And then we'll do list.map. And we're going to do, because it's the register, we'll map into that. And we'll pipe into this. Oh, I called it x86. Of course I did. Okay, so we can probably just copy all that, all the registers, and insert commas. I want to do this a sneaky way. Put initial commas in there, and then let it reformat. What's wrong there? We're going to do this very cheekily again. Okay, and then we'll put commas after all those. Oh, you didn't put a comma after those? Boo! I should have done on the left. Okay, stupid editor tricks. Okay, so we're basically just adding all the registers to the graph. So looking at the book again. Okay, so we add all the registers as nodes in the graph. And they don't have any edges between them because our edges are going to be conflicts, and we haven't determined those yet. Now, obviously, all the registers conflict with one another because they're like static locations, right? So we can't really give them anything and we can't assign a register a new register. It doesn't make sense. Okay, so the other thing that we're going to need to consider is what else is in our node, and I think we'll get to that eventually, but let's start by doing the algorithm that we talked about over here in the book. So if it's a move instruction, right, okay. So let's do rule 1b, because it's going to be the easier one. Okay, so we can loop over let's do set fold from, we're folding over the live set, and we're taking the graph as the input. And so we have graph, and we have a variable, so v. And this is going to be right. So you're writing d. So if v is d and v is not s, we've already ruled out that v can be s because it's immediate. So we can go, you know, it's funny now that I'm thinking about it, I could have done this with sets and not bothered with that explosion. Is it too late to back out of that? It's not. It's not. I don't know about you, but I often second guess myself. Now, we're not catching the case that would be immediate. and this needs to be, these need to be sets. Like, honestly, it's just, is there an intersection? Right? Or does this thing exist in one of these sets? Is really, like, you know, here you can say, oh yeah, if it's not equal. But the equivalent is it in the set? Because if it's an empty set because it's immediate, then no, it's not going to be in the set. If it is in the set, it's going to be a set of 1. Right? Yeah. Stupid tricks. Okay. Doesn't seem so like second guessing it was really valuable once more infinite. Yeah, absolutely. It's just that, like, I'm going back and now I'm like, why don't I just do it this way and then think about it harder? Okay, so we're going to do the same thing. We're going to fold over the live set and updating G. So G gets updated, and here's a variable, which is honestly a location. Okay, so if, and here's where it gets interesting. Okay, if variable is not in D and not in S, then add the edge from D, and this is where it gets a little bit tricky. So we're gonna have to do we have, because this is a single location, we have to do this let assert that, and like that'll give us our panic for the immediate, right? Because we need that. Like, we can't just say, now I guess we could loop through it. Maybe let's just loop through that set. There's only going to be 1, but okay. I need to stop flailing. So we are going to, this is an interference graph, we're going to have to add edge. So that's going to be something we need to insert. So we're going to say, let's call it add conflict. And this is going to be, A is a location, and B is a location. So, one of the things that we're not yet doing here is I want this insert location to be idempotent. Either that or we need to collect all the locations. My feeling is I'd like it to be incremental. Yeah, if I could only think harder, right? Very true. Okay. If it has it, right, then we'll return G. If it doesn't, then we do all this. Okay, that's simple enough to make idempotent, except we want brackets on that. Right. So if it, so then we can do, at the very least, we want this to add, let me say, we're just going to do this because this is a graph. We'll do set fold. Actually, we can just do insert location. That's pretty terse. Like it. Like it. Okay, so we need to make sure that everything from S and D and live is in the graph first. That was fun. Not too bad. Okay, so now we know that all of the live set and everything from D and S are in the graph. Like, this is a problem I was thinking about. Do we go through ahead of time and add all of the nodes through all the instructions, or we do it incrementally? We're kind of doing it incrementally here. It's not the greatest, I'm not going to lie. But this will make sure that when we go to add conflicts, which is what we were going to write, okay, that we know that it's in the graph. So we're going to do let assert, okay, A's ID is going to be dict.get from the lookup table A. And maybe I can give feedback to the author of this graph library and like, let us use anything for indexes, please. Let us use, you know, our own identifiers. Yeah. Okay, so yeah, it's just saying we're not using it. Okay, so we want to add a conflict from A to B, which is insert undirected edge, right? Okay, so we do so this is going to be graph.insert undirected edge. The label comes first, yeah. Label, we don't have a label. Nil is the label for us, we don't care. Hey, BID. And this takes g.graph as the first argument. Okay. So what we're doing here is we are doing do you not know what type this is? Oh, I need to label it. That helps. Okay, so we're taking the graph, we're adding an edge between these two things. So now over here, what we want to do is, so this is a location. What was the rule? For every variable or every location in the live after set, if it's not the source or the destination, add an edge between the destination. Right. Okay. So if so we want, if it doesn't contain, so this is S doesn't contain var, and D doesn't contain var. If that's true, then we do add conflict. And really this is just set fold or D with G interference, add conflict. We have to make a function for that. This is the graph. This is the destination. We want to add conflict in the graph between D and var. Whew. False. We just return G. Okay, so let's talk through this real quick because this is getting a bit confusing. Okay. We'll close up the Project Explorer and get these side by side. Okay, if an instruction is a move instruction of the form move queue from source to destination, so that's our source set and our destination set, then for every variable in the live after set, every V, actually it's not really a variable, it's just like what's live, could be a register. For every location in the live after set, if that location is not the source or not the destination. So in our case, that means because the source could be immediate, obviously it's not going to contain that because there's no locations in that. So I kind of want to reframe this as the or without the double. Let's say is, yeah, let's just redo that. It wants me to put brackets around them. I think that'll just syntactically look bad. Okay. So we'll add a conflict between D and the variable if it is not contained in either the source or the destination. Okay, I think that was hopefully clear enough. And that's for every live location. Okay, so now for the other instructions. What we have is a set of the right locations. So this is rule 2, set of the right locations and the set of the live locations. So this is like a Cartesian product. So we'll do something similar to this. So let's do... We want to make sure that, again, that all of these are in the graph. Okay. That might have been the first time I've heard someone else on a stream say the words Cartesian product. Yeah. Well, I was thinking of like, what was it? A number of years ago when I was watching one of your Rust streams and you were talking about like iter tools, there was a Cartesian product thing in there. Yep. Cross product? I don't know. What else would you call it? Okay, so we're gonna set fold. So this is pairing up every destination in the right set with every live after. Yeah, you still use that for Advent of Code? Yeah, I'm not surprised. Advent of Code has a lot of those sorts of problems. Okay, so we're going to fold over the W set, passing in G. And this is going to take G and we'll call it D, right? Because that's... Yeah, and then we're just going to do set fold over live. And this one will be a little bit simpler because we're only concerned with one destination, right? Or it's not a destination, it's the right set. V, we're using their variable names here. So case V not equal to D. If that's true, then we add a conflict into the graph between D and V. If false, we just return G, unmodified. Okay, so that one wasn't too bad now that we did the hard one. Again, this is Cartesian product because this could be any number of locations, probably at most 2. And this could be any number of live locations as well. Okay, and honestly, I think that's our whole algorithm. We don't need Gleam Erlang. Where'd you come from? Okay, so if we do this, this is going to be challenging to test, but we probably want some extra helper functions in here. And let's look at the docs for this. See, we could do has edge. So maybe let's make a has conflict. And this is between A and B. And this is a Boolean, right? So we'll do this same thing. And then we're going to do has edge. between AID and BID. Okay, so why I made this is that I'd like to use these things as test cases for our algorithm, right? So I'm pretty sure we used this one in our tests before in here, and then we'll use that to wrap up the stream. Again, we're still not to graph coloring. I'm kind of annoyed, but like it's really good that we get this correct. So let's look at our test here. Yeah, this is the one that we translated, right? So we know that let's just copy this. All right. So, oops. We're going to make a new test. And this is build interference. Test.gleam. Okay. Okay, so this is build interference. Okay, we're going to pop this stuff in there, and I think that we'll just copy as much of this as we can. Yeah. Why don't we copy all of this, and then we'll remove the stuff that we don't need. Okay, don't need that. So, this is going to be P. So this is our input program that we already verified in our other test is like this is the correct live after set. So what I want to do is do let P2 and I'm not going to test equality here. What I want to test is and we don't need to pipe that. What I want to test is the conflicts, right? So we want to make sure that we get the correct set of conflicts. So I'm going to extract that now. Let's do let assert okay block is p2.body and we'll get start. Okay, and then we'll do let conflicts is block.conflicts. Okay, so I'm going to import the interference graph, and I'm going to abbreviate it. Okay, so now given that, we can start writing assertions. So we can say that so if like V interferes with RSP, can I copy this whole thing out? Yeah, and I'll just comment it all out. Oops, I didn't get everything. Okay. So let's make an assertion for this one. So we know that V interferes with RSP. So we're going to do has conflict and right. Location var V. Here, we're going to say conflicts. Location register RSP should be true. Conflicts. Okay, and then we're going to duplicate that for these. So W interferes with V and yeah, let's do the first like so. And then V will also interfere with RSP. I was thinking a while back about, you know, what would be the proper way to test this. I don't want to test the implementation. I want to test the side effects of it, or like what's inspectable, because the graph data structure is going to be too complicated. I don't care about the implementation details of the graph, at least not at this level. Okay, so we're going to have a conflict between X and W. Now, some of these might be duplicate. We'll find out. Okay, and X has a conflict with RSP as well. Okay, so this is, again, the same thing. So we don't need to duplicate that conflict. Here's an interesting one. Okay, so we know Y interferes with W and RSP. So there's RSP. And it's going to interfere with W. Interestingly, I don't know if you've looked at that code, but for this graph package, when you have an undirected graph, it just adds the extra edges when you add an edge. So it adds the incoming and the outgoing edges. Okay, so Y interferes with W and RSP, okay, but not X. So we're going to do this, and this should be false. Okay, off we go. So Z interferes with W, Y, and RSP. So we got RSP, and it interferes with W. And it interferes with Y. And we just covered that, right? Y and RSP again. Okay, for this one, T interferes with Z and RSP. Okay. And again, T interferes with Z and RSP. Okay, RAX interferes with T and RSP. That's different. So this is going to be T. Let's make this a register. And this is going to be RAX. And Yeah, so there's a thing here where maybe we should go ahead and create conflicts between all the registers, but I think practically speaking it doesn't matter. Let's see if this test passes. Okay, interesting. So that passed. That's good. Okay, so so let's look at our other example here, like this one. Now we're going to have to figure this out ourselves, these comments. So okay, and then we'll get rid of P2. Okay, and I need to put call queue back in here. Okay. So let's go ahead and do the other bits of stuff that we were looking at. Okay. So thinking about this, let's write out. So call queue. This is call queue read int. And then we have add queue 42 RAX. And then we have jump conclusion. This one should be easier for us to deal with, but we're going to have to think about it. So if I recall correctly, the thing about call, we consider all the caller saved registers to have been written to. So the ones that, so an edge is added between every live variable and every caller saved register, right? And that comes down to the write set, doesn't it? So over here, no, interesting. These are the callee saved. Is that correct? Let's go back. To the bits that we're talking about the calling convention, and then we'll wrap up for today. Okay, so those are the argument registers. The caller save registers are all these. Callee save registers are these. Okay, let's go back down here. I don't have a split on this, but unfortunately. Okay, so for the call queue instruction, we consider the caller saved registers to have been written to. So an edge is added between every live variable and every caller save register. Live variable. This example doesn't have any live variables, right? And RAX is a caller save register. The other thing that we need to take into account, and possibly here in the interference graph, is if those locations are equal, where you just return the graph. Because you can't add a conflict with itself. Right? And yeah, this doesn't matter. Like, honestly, we could avoid the lookup, but it doesn't matter. But if two locations are equal, you can't add a conflict between them. That's one thing I needed to make sure happened. Yeah, so in this case, honestly, I don't think this is that interesting. I think it really comes down to, we just have, in this case, we have conflicts between RAX and RSP. That's all it is. Has conflict. So this is conflicts RAX. Those will be the only ones that will be created by this process, right? Be true. Now, what I might do here is, just for curiosity, let's debug conflicts. I want to see what it is. It's actually not that helpful, but you can see there's some edges there. So RSP has edges to node 3. Node 2 has no edges, and that's RBP. Node 3, here it is, node 3, edges to node 1, that's RAX. Yeah, so that's what I would expect. And again, there's not a good reason to explicitly put conflicts between registers. At least not at this phase. Okay. Wow, what a day. Let's have a look at our diff here. Close all. So, right, so we added the graph library. So we can collapse those. Okay. So maybe I should have made a commit after we did this refactor. But here we are. Okay, so this was just about moving those out and adding the new file. And then we removed the translation, which was nice. And again, we were just moving those into the new module. Same there. Same there. Oh, and I guess here we could have done... Yeah, it's fine. One thing we'll do before before we quit, as I'll show you the generated Erlang code because I'm sure it's interesting in these cases. Okay, and then we were just making those. Right, so we made sure that the number of live after sets matches up with the number of instructions. We made that public so we could reuse it. And the tests. Test, test, test. Okay, and then here's the interference graph. And there's the new base one, and then we have the new pass and the test for the pass, and that's everything. Okay, so this is chapter 3.3, I believe. Build interference. Also refactored the location and register types into a shared module that cuts down on some boilerplate. Okay. To cut down. Okay, and we're going to push that. All right, that's a good place to stop. Next week, I definitely want to get to the graph coloring. What is going to be interesting about that is that our graph, the nodes in here, are going to get information about what their conflicts are. Not in terms of the edges, but like what things they cannot be, right? So, and we'll get to using their mnemonic for naming locations with integers. The neat thing about this is it's going to go and let us see when we're going to spill onto the stack. So like we'll use all the available registers, general purpose registers, and then when we run out of those, if we do, we'll start to get stack locations. And so that's going to be a really neat algorithm to talk about. One of the things that's really nice about this algorithm, as they walk through it in the book, is that there's no need to do backtracking in this algorithm. So we'll have a priority queue, and things may move around in the priority queue, but it's going to be super interesting discussion, I think, and hopefully we'll get farther. We had to do a bunch of refactoring today, so we didn't get to some of the stuff that I wanted to, but this is still really interesting, and I think we solved some good problems. So thank you for sticking it out with me, and we'll see you next time.